All right, last bromination reaction, last radical bromination reaction that we're going to talk about is allylic bromination. And in allylic bromination, we are going to use N-bromosuccinimide as our reagent, so NBS, right? So you'll never see N-bromosuccinimide written out. It'll always just be NBS. You can also, of course, have chlorinated versions of this. If you have N-chlorosuccinimide, that is, of course, NCS, right? And it looks exactly the same, except it's a 5-membered ring, 2 carbonyls, and then the nitrogen chlorine bond, right? You can also, of course, have N-iodosuccinimide, that's NIS, all that other stuff. But notice what we have here is we have this sigma bond between 2 heteroatoms. And so that's our clue that this is a radical initiator, right? And so NBS, when we treat it, when we shine light on it, is going to be, that's going to be our initiation step. We're going to, this heteroatom bond will undergo homolysis. All right, so that's the bromination, that's NBS. Now we need to talk about what does allylic mean. So an allylic position on an organic molecule is a position that neighbors a pi bond. Right? And allylic positions are very special because, excuse me, they um, tend to have resonance stabilization of cations, anions, or radicals. And so allylic positions in general are going to be more reactive than other positions because if you make a positive charge at that position, you can have resonance stabilization. If you make a negative charge, you can have resonance stabilization. And important for us today, you can also resonance stabilize a radical at that position. So if we have this compound here, we treat it with NBS and light, right? The first thing that's going to happen is going to be our initiation step. So NBS is going to undergo initiation. The nitrogen bromine bond will undergo homolysis, radical, radical, right? And so what we'll get out is we'll get out a bromine radical. And we're going to get out the nitrogen radical. And I'm just going to abbreviate this a little bit. I'm going to say there's 2 R groups attached to that nitrogen, and we're going to have a nitrogen radical there. Right? So, whatever, fine. What's going to happen is we're going to remove a hydrogen. So remember, when we first do initiation, the next thing we're going to do is get rid of one of those radicals so that we can, right, we want to make a carbon radical or get rid of one of these radicals, and so it's going to go get a hydrogen from somewhere. So this gets a hydrogen from there, and we generate this tertiary radical. And it's not just a tertiary radical, but it's also a tertiary radical at an allylic position. Tertiary radical at allylic position. And so this is not just a tertiary radical. It also, if we move some electrons around, right, we can draw a resonance form where we move this pi bond over. Now, resonance forms of radicals are a little bit different because, of course, we can only move one electron at a time because we have this unpaired electron in there messing everything up. So in the past, you would just move that pi bond over, like if that was a cation, you'd move the pi bond over to add electrons to that position, etc. We can't quite do that. So we're moving electrons one at a time. So we're moving one electron out of this pi bond to make a new pi bond between these 2 carbons. Oops. And then the other electron that was in that pi bond goes to this end, this primary carbon on the end, and we end up with a single electron in this primary position. So we have a tertiary radical at an allylic position that is in resonance with a primary radical at an allylic position. Okay, so, and now you're probably thinking, well, a primary radical, that's not very stable. This is, this second resonance structure probably isn't going to form very much, but it turns out that this is actually the more reactive of the two, and so this is the thing that's going to react with the next equivalent of NBS. And what we get is a bromine at that primary position. Right? So once again, we're adding the bromine to the less substituted position. Right? So this is this keeps happening in these radical processes, right? The last two examples that we've done. When we add HBr, the bromine adds to the less substituted position. When we add NBS, again, we generate this resonance stabilized radical, and then we have a choice between a tertiary radical or a primary radical. And what's going to happen is we're going to add the bromine to the primary radical position. And so what we get here is we get a primary bromide. The bromine is added to an allylic position. Right? I think NBS reactions are a little bit hard to kind of get the hang of at first, but the thing, and so I'm going to do one more example, but the thing to remember is that once you make that radical, find the resonance, draw the two resonance structures, right? Because it'll always be a radical next to a pi bond, and then draw the resonance structure. So you're going to have two radicals to choose from. Choose the one where the radical is on the less substituted carbon, because that's the more reactive one. That's the one that's going to go get the bromine. So we'll do one more example just to show this one more time, and hopefully that will make it clear. All right, let's see if I can make a good example here. Okay, we're going to do this example where we have this double bond, and we're going to treat this with NBS and light. All right, so take a moment, think about where we're going to remove the hydrogen from to make their initial radical, and then what the resonance structures will look like and where the bromine will end up. So we know that initiation is going to give us a bromine radical and a nitrogen radical. And we know that we're going to take a hydrogen from the allylic position. And so we look at our allylic positions. There are no hydrogens here. No hydrogens at this allylic position. And so we can't take a hydrogen from there. So we have to take one from over here. So I'm going to do some quick eraser chemistry. Right, we're going to make that bond and make this primary allylic radical. Now, you may have concerns about making primary radicals, but remember that this is resonance stabilized, right? And so this primary radical is actually not too terrible because it has the resonance that kind of helps it out. So now we think about what are the two resonance structures. We have this primary radical here, or if we move the pi bond over and create the other resonance structure, we can have a secondary radical at this position. And so now you're going to compare these two. We have our primary radical here, our secondary radical here. Which one is going to be the one that reacts? It's going to be the one where the radical is at the less, goodness gracious, the less substituted position. And so this radical We'll come get the bromine, break the NBR bond, and our final product will be this one here. So we get the bromine at the primary position again. And so NBS installs the bromine at the less substituted position when you look at your radical resonance structures. And that does it for radical reactions. We got 3 reactions that we have learned. We've added Br2 in light is radical bromination, adds the bromine at the most substituted position. We have HBr and peroxides, right, which reacts a double bond, an addition reaction that puts the bromine in the less substituted position and the hydrogen in the more substituted position. And then we have NBS, which is allylic bromination. And the allylic bromination leaves the double bond in place, right? The double bond is still there in the product, takes a hydrogen from the allylic position, the neighboring position, and adds a bromine to the less substituted position of the 2 resonance stabilized radicals. So review those. There are worksheets that cover a lot of this radical material that are available on D2L. So make sure that you bring any questions you have to me at office hours, email, or come to one of the class meetings. Thanks.